Good afternoon, everyone. My name is Kunal Ghosh, and I received, as a professor said, I received my master's degree from IIT Bombay, and I've specialized in. I was a physical design lead and an STL lead while in Qualcomm and Cadence. And just last year, I have quit my full-time job and I'm doing this full-time. My full-time job in my own company. So before people ask me what I exactly do, let me show you a small video about what we do, because video will speak more than 1,000 words. Let's see this.
Hello everyone, my name is Kunal Ghosh and welcome to my new course on RISC-V instruction set architecture. This particular binary numbers enter into your chip or enter into your chip layout, and accordingly the functions are getting performed over here, and you will see the stopwatch behaving in the way it is expected to behave. So this interface are being called as the application binary interface, ABI, and this is a very important system call function that is present over here. Humans understand decimal format and the computers understand binary, so there has to be an interface that converts from something from decimal to binary. The entire 64-bit number is being called as the double word. So these four are really very important points with respect to the integers, and instructions which operate on these kind of numbers, they are called as base integer instructions, which is RV64i.
All right. So basically, that should give you an idea that we teach online. We are into online learning, and we have all sets of codes, right from RISC-V architecture to physical design to chip layout to clock tree synthesis, signal integrity, whatever blocks you can think of at the backend side. We have covered almost all the courses in form of online learning. So that's our specialization, and we have been doing this since past 7 years. And this talk at the back end, what we do, this is what we do. So basically at the back end, we are mostly into developing open source ASIC design flows. So we have so RISC-V architecture is at one level, and we actually match what they do. So they are into open source ISA, and we are into open source EDA. We take EDAs, we partner with open source hardware engineers, and we take their tools and try to implement and develop an ASIC design flow by ourselves. That's what we do at the back end, and it's a bit of funny. So while I was working in Qualcomm and Cadence, I had submitted a lot of papers in multiple conferences, and none of them got accepted. Only when I was starting to work in my own company, and suddenly papers started getting accepted. I don't know what worked out. So maybe believe in yourself and believe in the entrepreneurial spirit. That's the only message that I can give you. Okay, so back to business. The idea, the thing that we're trying to propose, or what we surveyed over here, was about the floor planning of a chip. So we took a E31 RISC-V core, which is about which was about, after post synthesis, was about 112,000 instance count design. But before even getting into the synthesis level, just when we get the RTL level, so what all analysis did with that particular design to make it compact and to make it high performance. So this is basically a survey of that. And while doing the entire survey, the entire analysis, we always use the open source EDA tools, and that's what this is about. So before starting into the floor plan, let me brief everyone about the idea of the floor plan. So how many from physical design? Anyone from physical design backend? Okay, couple of hands, yeah. So for each one of you, if I want to bring every one of you on the same page, so we start the way you do a ASIC, or the way you do an SoC. You start with the floor planning, and the idea of floor planning is that quickly I will explain you what is the idea of floor plan. So if you have this four flip flops and couple of blocks sitting over here on a real chip, you will definitely want D in to be placed close to the flip flop 1. You would want D in to be placed close to flip flop 2, close to block here. You want this D in 3 to be placed over here. You want the block B to be physically closer to the clock out pin. And that's the idea. So floor planning is the one that floor planning and placement are the steps that basically has taken care of this kind of scenarios, and this will basically make sure that you have the highest performance or the highest speed with a lower latency and the optimum area. That's the idea. So that's the idea of a floor plan. So typically I would in this case of floor plan, if you see D in 1 is being placed to the D in 1 pin, it's a port. This port is being placed to close to flip flop 1. D in 4 is placed close to buffer, but D in 4 is far away from D out 4. So the latency from if if a data has to transfer from D in 1, from D in 4 to D out 4, it has to pass through a chain of buffers, and that makes the latency even a bit longer. And another example is over here, let's say from D in 2, if it has to go to D out 3, the latency of the signal that will pass from D in 2 to D out 2, sorry, D out 2 is somewhere over here. So it will take some time to reach from one point to other point. So these are basically a couple of things that you need to be taking care of. And for example, if you see this one, the flip-flop 1, this flip-flop 1, and this flip-flop 2, the cells are almost abutted. So for this kind of logic, you will see the highest latency. And for a logic, let's say where this D2 wants to talk to D out 2, but the flip-flop is present over here, it will face the lowest latency problem. So these are the problems that needs to be taken care at a very early stage, and that's basically we call it as a floor plan. And so that is, and plus clock. So clock network needs to be built in a. So ideally we want typically of zero skew, but zero skew is rather close to impossible. So we go for a minimal skew that should be there between two clocks. I hope skew everyone should be knowing. It's basically the time needed for this clock to reach from flip-flop 1 to flip-flop 2. The time difference that it takes for this clock signal to reach in either of the flip-flops. The difference between that time is basically called as the skew. So the skew is again a very important parameter that needs to be considered before even laying out your floor plan, before even starting to do the ASIC design. So that's the brief overall general idea about floor planning and what this presentation is going to be all about. So we have done a complete analysis of the E31, and based on the couple of things that I've shown over here. So how does it help? So basically, if you look into, so for a physical design or for a STA engineer, there are a couple of analysis. There are a couple of performance analysis that we do along the way, and the most basic analysis are the reg to reg, the in to reg, the reg to out, and the in to out. So these are basically the most basic analysis that a chip designer does before a tape out. But if you really want to believe me, because I've been working for 7 years in the chip tape out, these are not the only analysis that as an STA engineer we have to sign off on. There are a couple of more analysis, and this is the entire list. So this is the entire list. So basically, you need to not only close on the first 4, you need to also be closing on the clock getting analysis, on the recovery removal analysis, and the data to data, the synchronous timing checks, the slew analysis, the load analysis, and the clock analysis. So these are the entire range of checks that needs to be done, and that is not only across one PVT corner. It has to be done across. While I was working in one of the companies, they had like 223 PVT corners. So this has to be done across all the corners, across all the PVT corners. And one of the violation, if let's say one of the checks failed, you need to rework the entire thing. And that is what we want to avoid by having the best floor plan as far as possible to the most ideal floor plan, which is not very close to reality, but we can always manage things and place the blocks before even going into the routing stage. We can place the blocks and the pins in such a fashion that we get rid of most of the checks at the initial runs itself, and there are only final 1 or 2 the last stages where we might want to fix only couple of fixes or couple of violations that needs to be done in the PVT corner. So that's basically idea of the floor plan. So idea of the floor plan is basically you need to be correct by construction. You start building the base so strong that while you go to the top, you might not face this kind of violations that you're seeing on my screen. Okay, so that's the basically top level idea of the floor plan. And so before getting into the E31 E-core complex, did anyone get what I just talked about, the idea of floor plan? Anyone can raise hand. Yeah. So basically, that's my profession. I teach online. So thank you. It worked. It looks like the images worked. Okay. So let's look into how does the E31 E-coreplex looks like. So if you want to look into the functionality of E31, I'm not the right person to look into the functionality. You might have a lot of people who can explain the functionality. And from a timing and from an implementation point of view, this is what I do. So I took up the RTL, which was available as an evaluation RTL on the Sci-Fi website, and just broke it down into multiple pieces, and this is what we came up with. So if you see over here, this is not a regular block diagram which comes out of the specification sheet. It's basically a floor plan. So physically, this block, let's say P bus, will sit exactly over here on a chip. Physically, this pins will be sitting at this locations itself in order to get the optimum speed or the highest performance that you expect from from a high-speed CPU. Physically, if you see the clock reset and the core clock, they have to come over here so that they can create a proper H tree. H tree is basically a clock tree algorithm. So it has to sit over here so that it basically branches out to each and every block from the center. And this is what we expect the system to do once you place your design something like this. E31, for example, has to sit somewhere over here where you see your pins like reset vector and the local interrupts to be coming from the right side. You see the debugs. There was a debug line. Yeah. So debug line has to be placed close to. It has to sit physically close to P bus so that the delay between the debug and the P bus is basically well maintained and the latency is well maintained. I'll show you one of the timing paths which clearly tells us that how critical the path between debug and P bus is. So that's basically more of a design knowledge. So the one who has a very good design knowledge, physically which block should be placed physical to which block, that decision needs to be done by a physical design or a floor plan engineer, and that's what we have been doing at the back end apart from the regular coursework. So let's break up some of the blocks over here. So for example, let's say if you look into the PLIC, which is a interrupt controller, you want the int X bar, the X bar which is present over here, it has to sit at the top. So let me expand this one. Yeah, so if you look over here, the int X bar needs to be, all the pins from the int X bar block should be coming at the top, and not only at the top, but towards the right hand side of the top, because that will play a major role for when you look at from the top level. It has to, the right side, the left side basically, this is the, so what we have done over here is for the int X bar is coming on the top, but we have actually covered this entire area. The sides that you see over here, these are the entire thing that we are allowing the int X bar to come, because if you look into the top level, int X bar is basically, there is no pins which is sitting on this side of the PLIC. So we prefer to keep the int X bar pins to cover the entire sides of the PLIC. Then we also prefer the P bus to be coming, the inputs on the top side and the outputs on the bottom side. This can be, you can use a different kind of permutation where some of the input pins can sit somewhere in between of these output pins, but in general as a whole, we wanted the P bus pins to be sitting at the left hand side. And if you see over here, the clock and reset is coming at the bottom. So when you try to implement a PLIC as a separate block, you have to make sure that the pins and the pin locations of the PLIC of this particular pins should be at what locations it is being mentioned over here. So that's the idea. Let's look into another example of a block. So for example, if you look over here, P bus. So P bus is interacting with the test indicator. It is being interacting. These are the clock signal. It is interacting with the debug. So ideally, the pins that is being coming for the P bus, that should be something like this. If you are trying to implement a P bus separately, so it's more of a hierarchical physical designing, where you take up each small blocks and try to implement them separately. And while you do that, you need to keep the pin locations as being mentioned over here. So for example, the right side, this is where the PLIC IO come into. So if you look into the previous picture, the PLIC is communicating with the P bus at this location. Physically, the pins of the PLIC should be present over here. Physically, the Clint IO should be present over here. The E31 communication bus should be present over here, and so on. So this is another example of how do you actually hierarchically implement the small P bus. And let's take into another example. Let's say we look into the Clint. Clint was a small block that we had, and the locations of the Clint will be as it is as being shown over here. We would like the P bus IO to be sitting at the top, which is the right side of the physical locations of the Clint bus should be present at the right side of the block. The in sync the synchronous crossing source should be at the right edge. This is where the reset and the clock comes over here, and so basically this is more to do with how does the physical layout of your each and every block looks like, so that when these blocks come together and assemble at the top, you should see something like this. You should see a picture like this, and if as expected, if you provide this kind of information to your any EDA tool, it could be any commercial or any open source EDA tools. If you give this information to your EDA tool, it more or likely towards almost 90% of the cases is that's the case where your top level chip layout will look something like this. If you place the pins over here, if you place all these blocks at these respective positions, more or less it will look, your top level floor plan will look something like this, and that's what we expect. We expect the latency to be optimum, and we expect the area to be optimum for this kind of arrangement of the blocks and the physical location of the blocks. we looked into another block which is E31. It was quite a bigger one. So E31 itself was again split into multiple blocks. We took the E31 block, so this was the exact pin locations of E31. The P bus was at the top. The S bus was at the left. And it had got a core clock which was coming from the top. So this was the exact pin locations of the E31. And E31 itself had got three major big blocks, which was, one is the front end, one is the core, and one is the D cache, which were slightly bigger than expected. So it was about 112 something 11,000 instance count or something in that range. So these were the instance count of these blocks. So we again took those blocks outside and implemented them separately, while making sure that the pins for the front end sat at the exact location where we expect the reset and the core clock to come into. And similarly, we took the iCache pins and placed it over here. We took the master crossbar pins and placed it over here. So it's more of a how do you arrange, or how do you floor plan, or how do you SOC plan your top level design, so that once you go to the bottom level, down to the routing level, you don't see much issues as the issues that we have talked about in the beginning. And some of couple of advantages and results. So by now, you must have learned that what we have done is we have just taken a large block and we have chopped it into small pieces and implementing the other pieces separately, and then we are concatenating the entire blocks at the top, and we are trying to fix the top level logic using this technique, and it has worked. It has done wonders. So basically, in my previous jobs where I was working and using the commercial EDA tools, I was in a position where I made the tool exactly the way I want it to be because of very good floor plan. So that's the advantage of having the best floor plan that you have, making the blocks, breaking up the blocks and placing it at the right locations. It's basically like you lay out your city. You want the buildings to be at certain locations so that these two buildings can talk to each other at a least communication distance. Similarly, that's exactly what you can think of those blocks as small buildings, and you can think of the lines as roads to reach to that particular buildings or apartments. That's a very granular level description of what I do. Now, advantages and results. So first of all, the first advantage that you will be seeing by doing a hierarchical break of this one. So for example, you can identify the problematic block over here. So if you look over here, when we did a flat implementation of the E31 E-core, we got a frequency of 74 megahertz, which was pretty low, and then we broke up the entire design into small pieces, and we identified that the other blocks were doing fine, but the debug one block was giving about 41 megahertz, which was very low. But when we tried to debug the debug block itself, we found out that it was reporting the tool. So basically we used all the open source, since we used all the open source EDA tools, the timing tool we used, it's called Vesta. So the tool is not that matured enough to report you the exact timing what we want to, but what it reported was the worst violating path was reported as a reg to out path, which for a performance evaluation, we actually take the reg to reg path. If you want to measure the frequency of any design, we basically take the reg to reg path, and unfortunately the tool was reporting a reg to out path, which is a separate kind of analysis that we do. So in order to identify the frequency, we always take the reg to reg path, and when we looked into the reports, when we looked into the timing reports for the reg to reg path, we found out that the actual frequency was 372 megahertz for this block. So because of the hierarchical nature of the implementation, it was very easy to identify this block, and we can just work out only this particular block. And then once you fix the frequency, or once you fix or change this particular block, you can just take that block, apply it, or just stick it to the top, and things will work the way you want it to be. That was one of the advantage of having an hierarchical implementation of this one. Second advantage, we found that it was a better performance. So if you see, the flat over here had given us a frequency of 74 megahertz, but if you went into the hierarchical approach, the slowest block, which will define the overall block, overall frequency, or overall performance of the entire chip, was about 145 megahertz. So it was almost half, and this was done using 180 nanometers open source process from Oklahoma State University, and we used all the open source tool chain. We used Yosis for synthesis. Anaga will talk more about the tool chain. So we used Yosis for synthesis. We use Timberwolf for placement. We used QRouter for routing. We used the Vesta for timing analysis. And there are again a few open source tools like OpenTimer. So OpenTimer is again an open source STA tool which you can use for all the static timing analysis things that I have talked about. So you can use actually the OpenTimer tool called as you can use the OpenTimer tool for doing your entire static timing analysis. So it was all that's the part that we want to emphasize on, that all these numbers that you see over here, those are completely based on the open source EDA tool analysis. So that's how these two things get married. So you have the RISC-V ISA, which is open source ISA, and we have our company that actually takes up or we go for fishing of the open source EDA tools and try to see which one best fits to get the best performance. That's how these two got married actually. That's the performance part, and that's one of the advantages. And if you see over here, there is a path from if you open up the timing reports, there is a path from PBus to debug, which actually justifies that the reason we had placed the block, it justifies that the PBus that was placed close to debug, they're actually communicating, and there is a lot of, it should be placed physically close to each other so that there is a very low latency between both the blocks. So that's the idea that we justified using the hierarchical nature of the flow. So that was about the bigger block. And again, these reports that you see, these are from Vesta. It's again an open source EDA tool, open source timing tool, which is being managed by Tim Edwards from OpenCircuitDesign.com. We got the tool from him. Next, basically, so basically, just in order to prove the entire thing, so the entire approach that we did for attacking a RISC-V CPU, it should be repeatable. So anyone has heard about the principle of mathematical induction? IIT, yeah, you must have heard about this induction. Okay, so it basically says that if you prove it for one design, if you prove it for the next design, it should be true for n+1. That's the idea. So let's try to prove it for another design. So we have another open source RISC-V core, which is PicoSoC. So PicoSoC is a small RISC-V core that was built by Clifford Wolf from Austria, and this supports RISC-V RV32 integer set instruction. So this was a small core that was designed by him, and we took that design, and we did the same hierarchical approach for that design as well. We took the Pico RV32, which actually implements the RISC-V 32-bit instruction. We took the SPI MIO, we took the simple UART, and we took the memory, and we just plugged and played, and we did the arrangement, what you see on my screen, and the numbers that we saw over here was this one. So PicoSoC flat gave us a frequency of 275 megahertz, whereas the slowest block amongst the four hierarchy was 407 megahertz. So actually 1.5x improvement we saw in the hierarchical implementation. So only disadvantage we see with the hierarchical implementation, that if as the number of blocks increase, you need more resources to do things. So more resources, by more resources I mean you need the more number of licenses. So for one EDA run, you need you might be needing 1 or 2 licenses. That's the advantage. You can do a lot of experiments using open source EDA tools, because it's just a matter of downloading the tools and running it for a number of times. So that's why that has actually increased our scalability. We got more hands and more tools to work on the same design. We got more minds to work on the same design. So basically, me and Tim Edwards, we both working on this kind of analysis. So it just increased number of hands that we can do using open source EDA tools. And finally, the forthcoming research that we are planning to do. So we have done like stage 1 of the entire thing. The second stage that we need to be achieving is that maybe by the next RISC-V workshop, you might see a chip which is being taped out using the entire open source EDA flow. And the next step is we want to improve the hierarchical placement and routing of the Q flow, because right now Q flow is very good for flat implementation, because there is a company called eFabless.com where actually we have taped out a chip, a PicoSoC. We have done a flat implementation using the XFAB process, 180 nanometer process, and we taped out using entire open source tool flow chain. So we have done that in the past, so we know that the Q flow works very well for a flat implementation. That needs to be extended. The existing infrastructure, whatever we have, that needs to be extended to support for the hierarchical design. That's the next challenge that we are targeting over here. And again, if you want to understand how did we actually implemented a flat design using open source EDA tool, there are a couple of courses that you can see on my website. So there are webinars which says that, which actually shows you online how did we did the entire flow. You start from RTL netlist, not even netlist. We started from the SOC, basically placing the analog blocks, placing the PLLs and all those interfaces. We started from SOC planning. We went till RTL design, and we did the entire PNR till the GDS on using entire open source EDA tool. You can watch the videos online. Those are all available. That's one thing. That's a small area of improvement that we are looking forward. Second area of improvement is right now the numbers that you see for the timing. Those are from Vesta. It's a Plan B open source STA tool. The Plan A was to use OpenTimer, but unfortunately there were some issues with the OpenTimer tool, which we have actually worked out, and the tool is come out very good. It will be releasing in next couple of weeks, the version 2 of OpenTimer tool. Now it will be able to support the complex constructs that we have in the library. That's the plan, and they've got very good funding from one of the institutes, and that's why the OpenTimer tool is getting released in the next week. It will be going big time, and we are almost all kinds of analysis you can do using the OpenTimer STA tool. It's close to a commercial grade tool. If you go for the NLDM part, for the CCS part, there is some work that needs to be done, but we are very confident that we'll be able to get the OpenTimer tool from the team who is working in University of Illinois. So the person, his name is Sung Wai. He is actually recoding the OpenTimer tool to make it for commercial purposes, or at least for devices or products which is about 130 to 180 nanometer range. So that's the second area that we are actually continuously working on with Sung Wai from University of Illinois. The third idea is that's just an idea which might get into the real scenario very soon. We want to do a real process. This is a place where some of you can help or can come forward to talk to me about this. We want to do the entire experiment using real process like TSMC or Intel or some of the global foundries, any real process. So the idea is basically to get the real process and take it through the entire implementation flow, entire open source implementation EDA flow, and do the same chips, the same PicoSoC and the same E31 using a real process, so that maybe by next some of the other upcoming RISC-V workshop, we might see some real chips that is being coming out of real process using open source EDA flow. So that's the vision. That's the vision that we have since 2 years down the line. That's the plan that we have set for our company, and we are partnering with multiple open source EDA vendors and tool owners to achieve this goal. So that's about my company. That's about me, and that's about what we are doing in the front end and the back end. I would like to publicly acknowledge Tim Edwards, who has been helping a lot towards developing the entire open source EDA tools. So basically, he's a guy whom you talk to if you want to get a PNR tool. And there are a couple of things that I get the tool from him, and I give him some suggestions. I run my own test suits. I have a couple of like 100 test suits which I just run using his open source tools. And then we talk a lot. We have been talking about for last 2 years and developing the tools and bringing the tools to this stage has taken up some amount of years. Now it's at a pretty good position for the flat implementation. The hierarchical part is something that we are looking forward to, and he's also a senior VP of the analog platform eFabless.com. So eFabless.com, basically you go to the website, you plug in the RTL, there are some buttons. You just click on place, route, synthesize, you click on LVS. So it's a basically cloud-based open source EDA platform. So you can go there. You need not worry about the installation of the tools. You need not worry about what goes behind and everything. You just need to log into the website, click on the buttons, you synthesize, and you place, route, do post-timing analysis, you do LVS, GDS, DRC, everything, and you get a chip, you get a GDS out of this particular platform. So that's again a very good platform. I'm partnering with the team based on my findings. So our works actually overlaps a lot, and that's how I've been helping them. We have been working together towards this approach, and that's all I had. So a lot of regarding the open source EDA tools and everything. Anaga will talk about. So basically, we need to make money, right? Based on the startup that we have, we need to do some. There is a business model that we work upon, and Anaga is going to talk a bit about that. All right. Thank you, guys. Thank you for being awake, and over to you, Anaga. Thank you.
Yeah, I don't see any DFT kind of implementation with the open
Sorry?
source. DFT.
Sorry?
DFT.
DFT not yet. There is a person, he's working from Noida. It is not plugged in yet, but he's continuously working on getting DFT in the open source domain. It will take time because this has just started. The hierarchical, the flat we have just finished, the hierarchical is about to start. So it will take some time, but it will definitely, I'm very confident the pace that we are going, it might definitely happen.
We tried to do with USIS and some of the already present in DFT tool, but it's still not supported.
Okay, so we can connect online. Can you give me some idea? I will note it down and we can do it. Yeah. So glad to know that there is something work that is already happening in DFT.
Yeah, we tried, but it's not possible. Like we are not able to insert it after from the netlist which is coming from the USIS.
Okay, you bring it to us. We'll make it possible. We are damn confident about that.
Hello, friends. I think it's time to wake up, so I will play a video for you. Hi, I'm Anagha. I'm an electrical graduate from Mumbai University, VGTI, and I worked in Tata Power for a long time. I'm completely not from VLSI background, but I'm an electrical engineer, so I understand circuits. So I helped Kunal to build this company, and the primary role in this company is just very simple, is to listen and to read. I hope everyone is awake to listen to me. Yeah. So I listen to students, to market, to community, to understand the needs of the market, what exactly they need in this industry. And we started, I can tell you, I'll just walk through our graph. I'll walk through our company's graph, which exactly tells you how we started and where we are heading towards. We started not like a blogger. We started like a very basic student. We used to draw all the diagrams, hand-drawn diagrams, the major concepts, the major big complex structures of VLSI design into small diagrams in the fashion so that student understands. And they can learn very nicely, and they can reproduce it when they are doing those designs and actually working to make some good products. So later, after building the concepts, we realized we need to make very proper make some content-wise presentations so that students who want to learn a particular concept, they will just have to target that presentation and they can learn from that. That was the era where I can say 2011 or 12. That was the era where was a boom ki video is the next big thing. Coursera, I think Khan Academy, or Mr. Anant Agarwal from MIT University, they had started all this edX and Coursera thing where they promoted online education through videos because they realized the next thing that's going to change in the education industry is videos. So we started making videos on those concepts. But we realized that making videos is not going to help a student to understand the concept. We need to give them an hands-on experience with the tools. That was the time when we started associating with open source EDA tool owners. And at that point, we got to know a website called efabless.com. They were also having a similar vision to bring an open source environment or develop an ecosystem where students can enjoy designing by using the free and available tools, which are not, where they can use their concepts, make more ideas, make more designs, and bring up new products. Yesterday, during the panel discussion, we were able to listen to lots of, I can say, backfalls, like why we are not able to go ahead and make some more products, make some more designs, new products. The reason is, I think there was less accessibility, or people were not knowing where are the tools, how the tools are. So this eFabless had played a major role here. They have bought a cloud platform where they have put all the open source tools there. They have made a proper GUI where a student can just plug and play with their designs, make a designs, and they have also collaborated with a foundry, XFab, I believe, right? XFab, and they have collaborated with a product company, Dialogue, right? Dialogue and Greenpack, where they are making some products by using those open source IPs. And after that, when we were working with eFabless, we got introduced to RISC-V. Mr. David Patterson, he mentored us to learn RISC-V, to make design courses out of it, and we also have, as Kunal showed you, we have a course on RISC-V ISA, where we have taught about the concepts, about the designing part, and now very soon Kunal is going to work on the E31 core also, since I already started working. I think we are the only one in today who is having an online course on RISC-V, and this helped us to cater to the globe. And I can proudly say our courses are taken in 131 countries, and I think that's around more than 16,000 students are taking our courses, and I believe the journey has just begun with RISC-V. To take this ahead, I will tell you how our vision and RISC-V vision is coinciding, like how we have similar visions. I was just sitting to just understand how RISC-V and we are similar, so I was able to jot down some points with them, with myself. At VSD, we always promote open source to the community who are taking our courses, who are taking our content, or who read our blog. Our website is having blogs on each and every topic that has been taught in our courses. So the people who can't take courses, they can just read our blogs because it's all open. And similarly, RISC-V is also born in an academy where it is born through the research done by the professors, by the students, by the community. Next is, at VSD, we have initiated a movement that we call as design at $0. That means if any particular student or any hobbyist or a designer who is wishing to design a chip, he should not have a hurdle of anything in front of him. He should be able to do it seamlessly. And the cost for designing should be zero. We are trying to provide a platform where he can do anything, but he can design a chip by using a zero penny out of his pockets. And I believe RISC-V is also similarly doing the same thing with the ecosystem. They have provided a free open source ISA. They have also given up so many cores and everything to the community to help them bring up with the more and more amount of work done across the RISC-V ISA. We at VSD collaborate with open source EDA tool owners and the community to design more and more chips, to bring more and more amount of SoCs built out of those chips. Similarly, RISC-V is also partnered with, I think, more than 174, as Rick said yesterday, to bring more amount of products from RISC-V core. As I would like to also tell, Kunal was telling you, we take workshops, webinars with this open source EDA tools. And I think RISC-V also conducts more amount of events, workshops, similar to the one which we are sitting here today. If I want to conclude this slide, I will say you RISC-V spreads technology, and RISC-V develops technology, and VSD, we try to spread the technology by using our blogs, by using our courses, by webinars, and reaching out to the students where they can learn the newest technology in the market. How we are trying to take this technology ahead, we have planned one workshop, one conference. I think it is one of its first ever online conference in semiconductor industry. I think all the conferences that happen in semiconductor are mostly at locations in California, Bay Area, or mostly the areas where you have all those industries. This is the only conference which will be live online, where you can just join in from wherever you are, and you can try to display your work done in the field of RISC-V CPU core. Like, the primary focus of this conference is to bring up the work that has been done to build SoC using a RISC-V CPU core by illustrating the ways in the field of RTL, CTS, library characterization, physical design, PNR, floor planning, and machine intelligence. But the crux of this workshop, the conference is, everything has to be done through using open source EDA tools, which we are providing the support with this, on this platform. And the key feature I can say you about this conference is, the keynote will be given by the father of RISC-V, David Patterson, who will be telling us more about what exactly the future is set with the help of RISC-V, about the next CPUs, about whatever designs that will be taking birth with the RISC-V core. The second person keynote speaker will be Mohammad Qasim, the person who has designed the complete architecture of this eFabless platform, who has brought this open source EDA tools into the cloud. And the next person is Vijay Narayan. I think many people must be familiar with this person. He is the chairperson of ACM SIGDA. SIGDA is the Special Interest Group of Design Automation, which I think many of you must be knowing here. The other things are me, myself, Sung Wai, whom Kunal was talking about, the owner of the Open Timer tool. I invite you, all of you, to our conference to join and display all the work that you have displayed here to other people who are not able to join this conference because of physical constraint. They cannot travel here. But our students are there in 131 countries, so your work will be displayed to all those people who will be joining this conference. I would like you to, means if you, not you, you can spread the word across. I have a pamphlet here with me. I will hand it over to you after this conference. You can give it to your fellow students, professors. I request the professors to ask their students if they're interested to, they can join the conference. I request the designers, the industry people to come and promote their designs, their products in the conference. Thank you. Any questions, please ask Kunal.